Hi, I'm Ananya. I'm actually a high school senior, and I'm doing this research at the University of Central Florida in the United States. So my project was on Ceria Infused Nano Silk Fiber Patch Fabrication and Applications. So the reason I decided to do this project was to synthesize a nanoparticle infused silk patch to determine its efficacy and antimicrobial use. And so what I mean by that is that due to the increased and very rapidly growing issue of antimicrobial resistance in today's world, there's been a need for locally delivered and tissue-specific solutions. And this is something that can certainly be solved with the patch that I created. So essentially, this patch is a home-based, very easy to use, very biocompatible and sustainable patch, and those are the characteristics that I'm going to be expanding on in my presentation today. So as you can see on the left panel here, I'm first going to talk to you about Ceria nanoparticles and why exactly I chose to use these nanoparticles instead of anything else. So as you know, Ceria nanoparticles have two different oxidation states. They have Ce4 plus and Ce3 plus, and these are a result of their differing electron configurations. So this is kind of going to go into the chemistry of the particles, but basically what happens, as you can see with the diagram over here, it's not extremely important, but hydrogen peroxide is reduced, and that is how the cerium-4 goes to the cerium-3. So it gets reduced, and then what we're looking at in this project is how the reactive oxygen species are emitted from this process. So this kind of squiggly line there shows you how these reactive oxygen species are released. So we're harnessing those free radicals to essentially act in pathogen defense, and that's how we're going to kill bacteria and infections and wound healing and drug delivery and etc. So the next part of the patch is obviously the silk. This is like the base of the patch, right? We're putting cerium into silk. So this silk comes from Bombyx mori cocoons. And the reason that we chose the specific type of silk is actually four-pronged. So the first two are because of the first is because of its strength. So this is a very important characteristic of this type of silk because what happens is that it starts off in random coils, the configuration of this silk, and then as you treat it with methanol over time, what will happen is that these coils will transform into beta sheets. So this transformation and this configuration right here is why we are harnessing this type of silk, because we want it to be strong and adaptable to whatever surface we apply this patch to. And so the next two characteristics are its porousness and its surface area. These two sound very simple, but in this project, they're very important because when you have a porous and large surface area, that allows for more drug delivery. So it's kind of just basic things, but kind of combining all three of these characteristics together, that allows this patch to be very resilient, and that is why we used this type of silk. So to actually combine these two, we use the electrospinning method, which is a pretty novel and pretty rare method. But what happens with this method, as you can see in this diagram on the bottom left, so this is the apparatus. This is the typical electrospinning apparatus that I used. So on the left, you see the capillary tube with the needle. And basically, that's what it sounds like. That is where the silk solution is going to be inserted. And then this high voltage supply is applied to that solution. And that causes this solution through a Taylor cone configuration to spit out as nanofibers on the collector, as you can see here. So this is like an easy diagram in which you can see how it actually works. So then kind of moving on to what I actually did in the lab. So the middle panel shows you the procedural and methods of what I did, and then below that is kind of how I characterized it. So if we look at the top here, we have two rows. So the first row is basically showing you how I formed the silk solution, which acted as the control. So this figure here, you can see that these are the Bombyx mori cocoons. So I basically cut them up. Then what happens is that we need to extract the sericin protein. And the reason that we do that here is because sericin is known to have allergic as known to cause allergic reactions. And so we don't want that to happen, obviously, if this patch is going to be applied on the skin. So we want to boil these cocoons to extract that protein. So then what happens after that is we dissolve this solution into lithium bromide. And that is kind of where this random coil to beta sheet configuration starts happening. Then we do dialysis before finally getting our control silk solution. So then after we get that, we add the Ceria nanoparticles, and we added them at 10, 20, 40 different concentrations here. And that's a simple part, but then the electrospinning comes in, and that was the method that I showed you just earlier. So after the electrospinning happens, as you can see here, it's kind of small, but this is what the patch looks like, and this is a red background. So you can imagine that it's a clear plastic kind of type patch, and it's very easy to use. It's pretty small. So what we're going to do to form that is we're going to treat it with hydrogen peroxide, and not shown here methanol, which is, again, to strengthen the fibers. So that is exactly what I did in the lab. So then I'm going to move on to how I actually characterize this patch. So we use 3 methods of characterization: dynamic light scattering, the FTIR, and Zeta Potential, and also the SEM images. So this first graph here, you can see the DLS data, and in our initial kind of purpose, our engineering goal here is essentially to reach a size that reaches 0 to 10 nanometers. So as you can see here, we have achieved that goal. And with checking with DLS, we know that. And then through the FTIR, what we want to see a couple of things. So the first thing that we want to see is that the bond energies are matching previously published data to confirm the reproducibility of the silk. So what that means is that we check the bond energies at each peak, at each trough. We're essentially checking that these silk fibers, this is silk, this is not some other material. We're forming the right silk. And then the second thing is also at the peaks and the troughs, you can see the wavelength, and that shows you, again, that beta sheet conformation, which is very important to this project. And then we see the Zeta potential right here. And again, that's just measuring the surface charge of the silk. And so we wanted it to reach between -30 to +30 millivolts. And again, that is achieved right here. And so the last kind of part of the characterization was the SEM images, which you can see down here. And what we're really looking at is how tightly packed these fibers are and how thick these fibers are. So these 2 images kind of show you a little close-up of, these fibers being so packed together so tightly, which makes them strong and, again, adaptable and biocompatible, which is what we want. And then this graph essentially shows you the thickness of the silk mat, and it reached our goal. So now I'm going to go to the right side of the panel, and what essentially I want to show you here is kind of why we did this project, how it can be applied, and what we basically found. So in the discussion, again, I kind of just said it, but I'm going to review that, the hypothesis was accepted, and this patch was formed due to what we gathered from the 4 methods of characterization here. So we reached the 1 to 10 nanometers range, we reached the silk typical bonds and the beta sheet conformation, and we reached this tightly packed structure. And you can see here, if you zoom in, that this is actual pictures from the lab. So the first picture is the silk after the cocoon layer is taken off of it. So that is what we boiled, and then right next to that is the electrospinning apparatus in real life. So that's what we boiled this, took out the sericin, and then put the solution into this apparatus right here. And then that is the final patch. So the whole point of this project is really to determine how to solve a problem. So the problem that was posed in the beginning of this presentation was that the increased emergence of antimicrobial resistance, right? So we want to solve that problem. So what we're going to do is we're going to try to see how this can be tested on infected wounds and drug delivery. So some ideas of future work that I personally have about this project is diabetic wound healing, right? So diabetic ulcers, other types of wounds for people who have diabetes. So that could be very, very helpful there. And That's one of our main kind of applications of this project. So we really just want this to become a standard of care for patients, which they can easily, if it's an adhesive, take off the adhesive, put it onto wherever their wound is. Drug delivery, there has been a lot of research on tympanic membrane perforations, which are, rips in the ear, where you can also implement this patch surgically. So this patch is very flexible in what you can do with it, which makes it such an amazing project. So in the future, there's a lot of things that, as I said, that we can do. So the first thing that we're thinking of doing is that rather than using Ceria particles, we're thinking of using zinc oxide. And so the reason for that is that zinc oxide has a lot of the same properties as Ceria, right? But the uniqueness of the Ceria comes from the 4+ to 3+ reduction. So we're trying to see if zinc oxide will provide the same, if not better results. So that is one of our next steps. And after that, we're also looking to do some cell culture and various assays, which have been done already, but not personally by me. So I'm looking to do that next. And then the final thing that we can do, which I find the most